Speech processing, part 2. Now let's go over to speech processing. We'll see how spectral analysis is done to get the sequence of outputs V. Now what's shown in the figure is an utterance of the word yes. Each phoneme here, YES, corresponds to a state of the HMM, and we will assume for practical purposes here that the pauses are also phonemes. So we have 5 states involved in V. Now, these are discrete time steps. And this is a trace of the waveform when the word yes is being uttered by someone. And what's shown here is the FFT, the transformed signal. And these transformed signals are done separately for each discrete time step. And so this is the output vector at discrete time step t, which is V of t. Now this is the trajectory of V of 3 to time. I've shown V of t in 3 dimensions. In reality, it's many more dimensions. And this is where it begins. This is the initial time step. And this is after one time step, t equals 2, t equals 3, t equals 4, t equals 5, so on. And so this is how the waveform progresses through time in the high dimensional vector space of all V's. This, and finally it ends up at the final state. Now this is the sequence of states. It begins with pause and goes through the states Y, E, S, and back to pause. And we might assume that the initial pause and the final pause are 2 different states. Now, what's known is the sequence of states. It goes specifically through pause, Y, E, S, pause. It's not going to jump back from S to Y, for instance. That's never going to happen. What's not known is the transition time. So, how many steps does it spend in each phoneme? Y, 3 time steps in Y before it transitions to E, or 4 time steps, or 5 time steps. Likewise, how many time steps does it spend in E before it transitions over to S, and so forth. The transition times are not known. But let's assume that they are known for the subsequent analysis. And this is a temporary assumption. We'll fix it. So now let's look at how to estimate the transition probabilities and the initial probability. Okay, so we have the voice samples, and after the spectral analysis, we get the sequence of states. And the sequence of states here is 5, pause, Y, E, S, and back to pause. We could assume that the 2 pauses, the initial and the final pauses, are different or the same state. It doesn't matter. I'm assuming that there are 5 different states. The initial pause, Y, E, S, and the final pause. Now, since we assumed that we know how long the HMM stays in each state, we can easily estimate Pij. So Pij here is a summation over all ones. In other words, we're simply counting the number of times this St equals Si, St plus 1 equals Sj occurs. And how many times is it? For instance, if let's look at this transition from state Y to state E. It stays for 3 time steps in the state Y before it transitions to state E. Therefore, the probability of transition from Y to E is 1/4, and so this probability is 1/4 and this probability is 3/4. Likewise, it stays for 1, 2, 3, 4, 5 time steps in the initial pause before it transitions to the state Y. Therefore, this is 1/6 and this is 5/6. So here this is the expression for Pij. The numerator is how many times this transition occurs, and the denominator is the number of times the HMM stays in a particular state, St equals Si. Now, in this simple English word yes, the numerator is always 1 because it transitions from Y to E only once, from E to S only once, and from S to pause only once. So the numerator is always 1 for all states I and J. But in a longer English word, maybe you could have another transition from S back to Y or something, in which case this would not necessarily be 1. And how do we count or how do we estimate the initial probability? It's simply, we know that it starts with this state, and let's call it S1. So pi1 is 1 and pi I equals 0 for I equals 2 through n. We already know that the word yes begins with a pause and then followed by a Y. And we'll just index this as state 1. So here's Baum-Welch re-estimation. The E step is as follows. The forward algorithm and backward algorithms are applied to find alpha Ti and beta Ti variables. And then, using the expression we had seen earlier, gamma Tim is obtained for each state I, each time step t, and each Gaussian m for each state I. And then in the m step, we do the following. Pi1 is 1 and pi through to pi n is 0. We just saw that. Pij is estimated. Cim is estimated using the gamma Tim that we derived earlier. Mu im and lambda im are also estimated using the expressions that we derived earlier. And then the new values of P, Cim, Mu im, and lambda im are replaced with the estimated values, and the next iteration starts. We don't need to estimate pi because this is actually given. It's not even necessary to put that in the m step, because we already know that pi1 is always 1 and all the other pi's are 0. Now, before the training begins, after the spectral analysis is done, we don't know in reality how long the HMM stays in each of the states. Now, one simple initial guess is to assume that the HMM spends an equal number of time steps in each state. That's why it's called uniform segmentation. So the entire time interval from here all the way to here is segmented into equal segments. So this is our first stage of speech processing. We are going to train eventually hidden Markov models. So initially speech samples are obtained, and then spectral analysis is done to obtain the sequence of output vectors V1 through V uppercase T. And then we assume that uniform segmentation is done so that the HMM is assumed to stay in each state for an equal number of time steps. Now we begin the HMM training after uniform segmentation is done. So we have the estimates of the initial states, S1, S2 until S uppercase T. And then for each state, S1, S2 until S uppercase T, we estimate the Gaussian mixture model parameters. And then we begin the Baum-Welch re-estimation. So once the sequence of states is known, and we do an initial guess of the Gaussian mixture model parameters separately for each state, and then we begin the Baum-Welch re-estimation. CIM, μIM, lambda IM, and Pij. Then we apply the Viterbi algorithm to re-estimate the actual transitions. How long does the HMM stay in each state, S1 and S2 until ST? So the most likely sequence of state is obtained using the Viterbi algorithm. And then we check if the HMM has converged or not. If it hasn't converged, then we go back to Baum-Welch re-estimation. Now, here, the uniform segmentation no longer applies because we re-estimated using Viterbi algorithm the most likely sequence of states. And then we apply the Baum-Welch re-estimation again to obtain the HMM parameters and keep on iterating until convergence. At the end, we obtain the hidden Markov model for the English word yes or any other word, which is theta. The parameters are CIM, μIM, lambda IM, and Pij. And so this is what we assumed before training. We assumed uniform segmentation. Each phoneme was given an equal number of time steps. But after training, it's no longer the same. We now actually have a very good estimate of the amount of time that the HMM spends in each state. Now, here are the steps, or rather the stages of training. And it's a very simple version. What really happens is more complicated than this. First, the samples of several female and male voices are collected. So we have V, output sequence V, several samples of that are collected. And then each sample is pre-processed, spectral analysis. And then an HMM is trained for each word, L equals 1 through L. So for each word, like yes is a word, so we obtain an HMM for the word yes. And so we do the same thing for every English word. Now that's obviously not a very good idea for a general purpose application, but for instance, if the words are simply the numbers 1 through 10, then it's easy to do. And then once the HMMs are trained, and then this is how speech recognition is carried out. Here our task is to find out what word is being uttered. So an unknown sample, which is a voice trace, is obtained and spectral analysis is done. And this unknown sample pertains to a word. We don't know if the person is uttering yes or something else. And then the forward-backward algorithm is applied to obtain alphas and betas for each HMM because we don't know what's the word. So maybe theta L corresponds to the word yes, and theta 1 corresponds to another word, and theta uppercase L corresponds to another word. So the forward-backward algorithm is applied separately to each HMM using this unknown sample. And then that gives the probability of the unknown sample V. Probability of the output sequence being V if the word is the first word, and this is the probability of the output sequence being V if the word was yes, the English word yes, and so on. And then we simply take the argmax of P V given theta L for each L. The highest probability is chosen, and that's recognized to be the word that was uttered. The end.